let's take a look at a mass spectrum. This is what one looks like, right? Remember I said here's our M over Z, our mass to charge ratio on X, relative abundance on the Y-axis. This is always scaled so that the highest peak is 100%. The numbers themselves aren't anything absolute other than relative abundance compared to that one highest peak. So let's start with the peak that has the largest mass. The one at 44 in this case is called the molecular ion peak. And this is the mass spectrum of propane, right? CH3, CH2, CH3. That's just propane. The molecular ion is when a propane molecule is struck by that electron beam and gets just one electron removed. So I'm going to show plus dot just outside of that whole molecule, meaning somewhere in that molecule one electron has been removed. We're not going to specify where exactly, but that's why it's called a molecular ion. It's the whole molecule that's been ionized, so it can actually be sent through that mass detector, right? So typically the particle with the largest mass is the one that we call the molecular ion peak. This one corresponds to M over Z of 44, and propane has a molecular weight of 44 AMU. So by looking at the molecular ion peak, we can tell what the molecular weight is of the sample that we're analyzing. So that is the first, probably most obvious piece of information we can get from a mass spectrum. What is the molecular weight of this molecule that we've just made? Notice that we have several peaks that are less massive than the molecular ion peak. All of those correspond with the fragments that were formed. Originally, when the substance was hit with those electron beams, sometimes the molecular ion was formed, but a lot of times this molecule fragments. And those less massive ions are sent through the mass spectrometer, sorted by their mass, and plotted against their abundance, right here. So what's called the base peak is the peak that has the greatest abundance. So that's going to be this one. The base peak will read 100% relative abundance, and all the other peaks are shown relative to it, right? Just basically some instruments can give us a little more information than this just at the first level. Some more precise instruments can actually record masses to 4 or 5 decimal places. Even though on this one it just looks like it's 44, you can go into the software and it'll tell you that it's 44.01498 or something like that, AMU. The exact mass of that molecular ion can allow you to differentiate between formulas that have close molecular weights to each other. So, because the masses of these atoms are not exactly on the dot in terms of AMU, right? Carbon-12 is exactly 12, but everything else has a little bit of a deviation from that, right? So oxygen-16 is not exactly 16, for instance. So for that reason, take two formulas, C5H12, C4H8O. Both, if you added up their molar masses, they'd be around 72 for a molecular weight. If we use exact masses, though, we would get 72.0939 for the hydrocarbon, 72.0545 for the one that contains oxygen. So the software in these mass spectrometers can actually use that exact data to calculate the closest chemical formula for you from that. So all that comes just from the molecular ion peak. Be careful, these exact masses do not come from the atomic masses on the periodic table, right? On the periodic table, that's the weighted average of all the isotopes, but the mass spectrometer separates out isotopes from each other because carbon-13 weighs 1 AMU more than carbon-12, for instance. So when we added up these exact masses, we only took the most abundant isotopes. So carbon-12 and oxygen-16 and so on, right? 1H, hydrogen, protium, if you want to call it, instead of deuterium, instead of the other isotopes. So the minor isotope contributions do lead to small peaks that are more massive than the molecular ion peak. These are referred to as M plus 1, M plus 2, etc. And if you look closely at this mass spectrum we have here, the molecular ion is this one right here, but you see a tiny little peak next to it, 1 unit greater in mass, that we call M plus 1. And since this is just a hydrocarbon, what that M plus 1 refers to is 1 carbon 13 that has been represented within this molecule. And as you did in your lab activity, you saw that the more carbons you have in your molecule, the more chance you have to get 1 carbon 13 incorporated somewhere. So there are techniques that take the height of that M plus 1, and you can get some information about the number of carbons, but we won't deal with that too much anymore at this point. But be aware that this tiny little peak here represents those minor isotopes that can be incorporated within the molecule. So let's take a look at some of those fragments that were formed when the sample was ionized. Looking at these fragmentation patterns will give us much more information about the structure beyond just its molar mass or its formula. It turns out that lots of fragmentation happens, and there's a lot of sort of bizarre things that happen that can't be quite as easily predicted, but one molecule will fragment pretty much the same way anytime that same substance is run. So that means that that pattern of fragments that you see in a mass spectrum will give a fingerprint of that molecule. So if you have a known sample of that substance, you can match it to do a positive identification. One way that substances are identified that's very important in the forensic sciences, where a very small trace sample, for instance, is analyzed for its components. This is actually a common method that's used to detect propellants in arson investigations, for instance, or toxicology on blood samples to find very minute amounts of chemicals within the blood. Can use mass spectroscopy that way. So let's talk about this fragmentation. When the radical cation fragments, it produces a radical and a positive cation. So two parts to it. The radical cation we start out with, one fragment gets the radical, the other gets the cation. And it's very predictable to figure out which one will go to which, because the more abundant peaks will come from the more stable carbocations. So what we're ultimately going to be looking at is where we can fragment a molecule in order to make a carbocation. So look at this neopentane molecule, 2,2-dimethylpropane. Its base peak is at 57, which means it's most abundant, remember. Very tall base peaks normally correspond to very stable carbocation fragments that are formed. So here's our molecular ion. A fragmentation happened, right, where we broke one of the carbon-carbon bonds. So a fragmentation is the breaking of just one bond, so I'll choose that one. And since this was a radical cation to begin with, we could imagine that this bond may have just had one electron in it or something. That's one way to think of it, but that would leave a carbocation on one side, a radical on the other side. We specifically choose to make useful to us the side that will give a very stable carbocation. This is a tertiary carbocation, which, as we know, gives a much more stable structure than a secondary or primary. The other fragment is this radical, but it is neutral. That mass selector requires the particles be charged so that they are able to be influenced by that magnetic field. This neutral radical is not observed in the mass spectrum. Okay? Neutral molecules will just continue flying straight, whereas the cations, like this one, their trajectory will be deflected by those magnets. So the stuff that just flies straight just goes out as waste, but the positive ions that are deflected, those are the ones that are able to be selected by their mass. So it makes perfect sense that the most abundant peak here will be at 57, because that is a stable carbocation. That's actually more stable than this molecular ion itself overall. So let's take a look. Here's hexane, molecular weight of 86. Here is its mass spectrum. We see the molecular ion right here as the most massive particle, not the most abundant, definitely the most massive. We see a small M+1 next to it, corresponding to carbon 13s. There's 6 times the probability of incorporating a carbon 13 in here than if there were just the one carbon. So as we get more carbons, this M+1 ends up getting a little bigger. The base peak here at 100% is at 57 AMUs, right? You can just look at the scale here and see it 57. So we're going to be able to figure out where that comes from. But when I have hexane, when I have just some sort of hydrocarbon like this, the whole thing is 86. Let me just show you a way to draw mass spec fragments. I drew sort of a bracket pointing inwards, showing that this whole thing is 86. If I were to break this carbon-carbon bond, what we would end up with is removing a CH3. So we remove 15 from 86, that's 71. That corresponds to that peak right there. That is minus 15 units, right? Or we can write minus CH3, where we fragmented a methyl group off of the end of it. Okay? That got us to 71. Going from 71 to the base peak is a difference of 14. 71 minus 14 is 57. That should correspond with removal of a CH2. So there's 57 right there. Turns out it's still a primary carbocation, but for whatever reason, that one has become a little bit more stabilized than the others. And like I said, there's a lot of other weird things that are happening. So if we can rationalize some of these peaks here based on normal fragmentation, then we've got good evidence. So same thing is going to happen again. Removing another CH2. 57 minus 14 is what, 43? Well, 43 is right here. There's loss of another 14. And then finally, loss of another 14 is 29. Corresponds with just CH2, CH3. So chipping away at it like this can show you this kind of pattern that's formed. Now, that's not the actual process that happens. The original ion could be split here, could be split here, could be split here, could be split here, right? A lot of different things are happening. So these are just all of those different ions that are coming in. Usually one peak doesn't split again after that, but when you have a hydrocarbon chain, you can just imagine chipping away one carbon group at a time. So you can always pretty much assume that there will be a minus 15 if there's any kind of CH3 in your molecule. If you've got a whole chain of CH2s, you'll have a series of minus 14s going along the course of the mass spectrum, getting smaller and smaller. Now, we do not have a final 15 peak because the methyl cation is far too unstable to be observed in the mass spectrum. Right? This 29, the ethyl cation, CH3, CH2+, is not tremendously stable, but at least it makes it through the mass spectrometer to the detector. So say we have two samples, sample A, sample B, similar compounds. You can tell the molecular ion has the same weight, okay, in both of these. Can give you a little more information. I have methyl cyclohexane. So let's draw these just to make sure we're on the same page. There's methyl cyclohexane and then ethyl cyclopentane. So both have 7 carbons, right? Both have the same number of hydrogens because there's one ring in both of them. So they both need to add up to 98. That gives us the molecular ion. Let's call that M+ on both of them. We should be able to use our mass spectra, though, to differentiate between those two compounds. And we're going to do it specifically by intensity of some of these fragment peaks. So start with the molecular ion. That was at 98. Remember what I said with hydrocarbons? Try subtracting 15. You'll often get a peak there corresponding to removal of one methyl group. So 98 minus 15 should be 83. All right, 81, 82, 83. Let's see if that makes any sense in our molecules here. Definitely methyl cyclohexane. The whole thing was 98. Right. If I remove a methyl group from that, that's minus 15. That should give us 83. This whole thing was 98. I can remove a methyl group from it. Get 83. I should also be able to remove another ch2 from this ethyl cyclopentane, right? Minus 14, so 69. I can, in fact, predict what the base peak will be in both of these. With the methyl cyclohexane, when I remove that methyl group, I end up with a cyclohexyl carbocation, okay? Secondary carbocation. When I remove ethyl from this ethyl cyclopentane, I end up with a cyclopentyl carbocation. I would predict each of these would be the base peaks. In fact, in this cyclopentane one, I would predict that the peak at 83 would be very small because it's a primary. That would be a primary carbocation. So, does that make sense? Yeah, here's one with a very small 83 peak. Okay. But then, if I take away 14, I get 69, which is the base peak on that one. 83 was the base peak on sample B. So that makes it pretty clear to us that the sample B was the methyl cyclohexane. The sample A was the ethyl cyclopentane, specifically because of the size of these peaks. 83 being cyclohexyl cation, 69 being cyclopentyl cation. I can't really do a whole lot beyond that because that would involve breaking open the ring, and that's a little more difficult to do. In our analysis of mass specs in this class, you should be able to do your analysis just by breaking one carbon-carbon bond at a time, chipping away at the molecule. And if a more stable carbocation can be formed at a certain point, expect that to be a much larger peak than the others, for instance.